Hello, I'm Jun Kim from the Department of Mechanical Convergence Engineering at Hanyang University in Seoul. My advisor is Professor Sewon Song. Today, I'll be presenting on the topic of machine learning for identifying vehicle design changes in wake flow. This research was conducted in collaboration with Hyundai NGV. During designing vehicle, wind tunnel experiments are conducted to measure and analyze the airflow, especially the wake flow. These experiments help assess the vehicle's aerodynamic performance. Variations in design lead to different airflow patterns, allowing the identification of design influences. This process balances design and aerodynamic performance, guiding design development. However, inconsistencies in analysis due to evaluators' experience pose a significant issue. Trial and error analysis is then utilized, increasing development time and cost. Fluid flow possesses complex high-dimensional and nonlinear properties, making standalone flow data analysis challenging. Similarly, AI excels at inspecting such characteristics from vast data volumes, and it finds applications across fields like fluid dynamics. Thus, I aim to address the consistency issue by creating an AI model to replace evaluator-based processes. To do this, input flow data and desired design influence output need to be defined. Here's the objectives of this research. This study aims to develop an AI model to identify vehicle design changes through wake flow data. So I researched the best form of input wake data for effective training of the AI model in predicting design changes. Two output labeling methods were examined. One is multi-level classification with gradchem explanations, and the other is multi-target regression. Employing these methods with diverse input data, I assessed the model's capability to predict design changes. Let's define the training ground truth data I used for the model. I employed data associated with the vehicle's design elements as the output data. Each vehicle comprises 15 design elements, denoted as D1 through D15 for simplicity. Varying the sizes of these elements allowed us to generate a variety of vehicle shapes, leading to the preparation of 72 vehicles. Following this, velocity and vorticity fields were acquired through wind tunnel experiments. Let me explain the wake quantities used as input data. In the wind tunnel experiments, by configuring the direction of the free stream in the plus x direction, we captured wake flow on the YZ plane at a specific distance from the vehicle's rear. This process yielded 72 velocity and vorticity fields, each with two dimensions and 3 components. Additionally, by computing derivatives of the main flow components, we obtained 72 gradient vector fields. This concept was drawn from literature that suggests scalar function gradients for effective edge feature detection in images. Since given data are symmetric and gradient has to be symmetric too, I utilized half of the wake fields. Although other physical quantities could potentially serve as input data, these 3 were selected as representative for this research. However, training an AI model with just 72 data is challenging, as meaningful models typically require thousands of training samples. Here I propose a strategy to augment the training data. My main focus is on the variations in wake patterns due to design element changes rather than the absolute values themselves. By selecting any two vehicles from 72, we can compare their design and wake data individually. This enables the use of wake comparison data as new input and design comparison data as new output. Consequently, this yields 2,556 data points corresponding to the combinations of 72 choose 2. This results in a significantly expanded and valuable training dataset. Additionally, I'll present two design comparison strategies and three wake comparison strategies. In this slide, I'll introduce the first design element comparison strategy, multi-level classification. Multi-level classification belongs to the classification domain. Binary classification predicts a single Boolean value, 0 or 1. Multi-class classification predicts a class for input data. Conversely, multi-level classification predicts multiple corresponding classes for input data. In this study, my aim is to identify changes design elements using provided weight comparison data. A design element with alterations between two vehicles receives level 1, otherwise 0. In this slide, I will introduce the three weight comparison strategies. The first approach involves using the main flow component difference, specifically the variation of UX, which had been utilized for evaluator-based analysis. The second is cosine similarity between two vorticity fields. Cosine similarity can quantify the similarity of patterns between two vector fields. For the third, similar to the second one, cosine similarity is calculated for the gradient vector fields of the UX velocity component. For model training, ResNet 18, a form of residual neural networks, was employed. ResNet is a convolutional neural network architecture developed for image classification. It consists of residual blocks, as shown below, which contain a structure to incorporate input-output information. The ResNet 18 model was augmented with a final layer producing 15 output values for design comparison. Training hyperparameters are as follows. Data was split into 7 to 3 for training and testing. Batch size was 20, with a learning rate of 0.0003 for 500 epochs. Now I'll show the results from training using the multi-level classification approach. Across the three predefined input data types, accuracy was computed. Here, accuracy signifies the proportion of correctly predicting all 15 design element changes within the whole dataset. Comparing the red test accuracy lines on the graph, it's clear that using cosine similarity of vorticity produces the highest accuracy. Similarly, for the third case, accuracy surpasses 70%. What we can observe from this result is using velocity derivatives and cosine similarity, which normalize data from minus to 1, may enhance the model's predictions. Additionally, I utilized GradCam to visually explain the predictions of this classification model. GradCam, short for gradient-weighted class activation mapping, visually represents a classification model's decisions on image by highlighting regions of interest based on model's gradient values. For example, if the model identifies an original image as a cat, GradCam emphasizes the image's influential reasons. This applies similarly to images of dogs. Below, you can see a few graphical results applied to our model, focused on predicting changes in design elements. These results pertain to the model trained using cosine similarity of vorticity, which demonstrated the highest accuracy, particularly for design elements predicted as true positives. So we can visualize where the model focuses on for decisions. Next, I'll introduce an alternative training approach and multi-target regression. Unlike classification's 0 and 1 predictions, here the focus is on predicting numerical changes in design elements. The goal is estimate the actual numerical differences in design elements between two vehicles. These normalized differences served as the output data. Similarly, I'll now share the results from training the model using multi-target regression with the same input data. Accuracy was assessed through Pearson correlation coefficient between predicted and actual values of the 15 design element differences. These coefficients were averaged for an arithmetic mean. Just like the multi-level classification results, successful training was noted with high accuracy using cosine similarity, particularly vorticity. Furthermore, we evaluated individual design element prediction performance through 15 graphs plotting ground truth data against predicted values across all test instances. Each point represents a single test data point, and points closer to the y equal to x line indicate accurate predictions. Color bar values indicate data density, with higher values signifying denser clusters. Given coefficients of 0.86 higher, we can confidently conclude accurate predictions for each element. In conclusion, we developed an AI model for analyzing and predicting the effect of vehicle design changes on the wake flow. So we trained Resonate 80 model using wake and design comparison data. Consequently, the most effective input data is the cosine similarity and vorticity fields, which achieves a maximum accuracy of 75.1% for multi-level classification and a maximum averaged Pearson correlation coefficient of 0.9445.